Welcome, everyone. Thank you very much for coming to see me speak. My name's James. I'll be talking about, well, Lego, Millennium Falcons, things like that. But there is hopefully a kind of semi-serious side to this talk. I'll be also hoping to introduce you to a number of methods we can use to help optimize the systems of work in which we spend a lot of our time. So my journey with this talk began 10 years ago. I first gave this talk. It was one of the very first sort of conference talks I did back in the sort of early days of my conference speaking journey. And it's based on a true story. And then about 4 years ago, I was asked to do it again as a keynote for one of our conferences. At ThoughtWorks, the company I work for, we have this conference called XConf, which we ran. I did it as a keynote, but I thought I'd revisit it to understand, over those 10 years, what I've learned, essentially. So what I'll be doing is I'll be going through, the sort of original sort of content, but then also my personal journey over those 10 years. So I've been at ThoughtWorks about 17 years in total now. I guess I've got about 25 plus years in the industry. You can see I have a grey beard. I am actually a grey beard, I also have a grey beard. And so this is kind of about the thing I'm most passionate about at the moment. I've been through phases in my career. I started off super excited about the nuts and bolts of software development, programming languages, these kinds of super deep technical challenges. And then I sort of became much more interested in sort of people and how people work together and teams. And then I sort of got more interested in software architecture and software design in the large, until finally I've sort of come back almost to this place. I feel quite zen in it, which is trying to understand how systems of things work, how systems of work, how flow works, how organizations work, how teams work in organizations. And that's the thing I'm really passionate about at the moment. And hopefully I'll be able to give you some insights from what I've learned over the past decade or more, working for many, many clients. But first, I should offer a disclaimer before we start. And that disclaimer is that ChatGPT played absolutely no part in any of this content whatsoever. So if you were hoping to get an AI-generated conference talk, you'll have to wait until next year, because I fully intend to have it write all my talks from now on. I did try and get it to write an intro, and it was pretty good, but I just couldn't bring myself to use it. But next time, all bets are off. So this is the agenda for today. So first of all, I'm going to do a brief recap on a number of things, right? So a brief introduction into Lego, what Lego is, a brief recap on Star Wars, and then a brief recap on flow and some of the tools we can use to understand flow on our teams and understand how we can measure flow, improve flow, and identify when blockages are in things in our systems. So first of all, is there anyone in the room who doesn't know what Lego is? No, we're all good. Legos, for the Americans in the room, if there are any. But Lego, no, we're all good. Okay, I'm what's technically known as an adult fan of Lego. I don't know if you've come across this designation. This is for grown-ups who still like playing with Lego. I'm one of those individuals. I watch Lego Masters on television religiously when it's on. And I buy those. I'm basically the target market for the giant sets they produce, right? The huge things. The last one I bought, which I was really pleased about, was it's the Ghostbusters fire station, which is like literally yay big. It's amazing. It kind of opens up. It's got all the ghosts. It's got the Ghostbusters in it. Fantastic. So I'm kind of an adult friend of Lego. I've been into Lego for a very long time. We've got a lot of it at home. But I'm also, turns out, a bit of a geek, if you haven't worked that out already. I'm also quite into Star Wars. I've been to, I watched Star Wars when I was a kid. All my friends were super into Star Wars, to the point where we actually, this year, end of last year, we actually got a box in the Royal Albert Hall to watch Return of the Jedi in concert, which is the most amazing thing. It's this huge IMAX screen with a full orchestra who play the soundtrack throughout the film. It was absolutely amazing. Turns out you need a lot of French horns in the orchestra. It's like a very French horn-heavy orchestra, the Star Wars soundtrack orchestra, but there we go. Has anyone not seen Star Wars? Surprises me, there's usually at least one. but no, everyone's good with Star Wars. There's a brief recap anyway. So episodes 1 to 3, we don't really talk about episodes 1 to 3. This is just not something that really exists in certainly my friends' part of the Star Wars canon. So we'll go straight on to episode 4. So episode 4, boy realizes he can do magic, falls in love with a girl. They have a fight with an evil empire, blow up a space station. Ben, oh no, Ben Kenobi dies. Episode 5, boy's mate gets frozen. That's not so cool. Boy learns how to do magic by finding some wise dude on a planet somewhere. Finds out his dad runs the evil empire, which kind of sucks. Episode 6, boy understands that he loves this girl who's been in the first 2 episodes as a sister, which is good, right? Because it was getting a bit awkward at one point there. He has a fight with his dad. He beats his dad. Then there's more fighting and the thing blows up. That's pretty much episode 6. Now, /S boy /girl, right, from this point on, right? Or /S Ben /Han. You'll see what I mean. Girl realizes she can do magic, falls in love with a boy, sticks it to the evil empire. Han, no, not Han. Spoiler alert. Episode 8, the boy from 4, 5, and 6 is back, but he's now the old dude who's the mentor on the funny planet that she has to visit, right? They drink puffin juice, it's all very strange. Leia dies, shock. And episode 9, wait, what? This dude was dead in episode 6. Why is he back? Where did all the ships come from? It's all very confusing, but a brilliant ending. And I am all the Jedi. Awesome, right? So that's Star Wars, right? We got Star Wars? Fine, good. That should be all clear. There's a recap on flow, right? So my definition of flow is how we optimize systems to keep stuff moving, right? And what do I mean when I say stuff? I mean stuff, all sorts of stuff. Physical stuff, digital stuff, information, right? The flow of these things is what enables us to, purchase goods from supermarkets cheaply because they optimize the flow of goods through a just-in-time supply chain, which keeps their holding costs down, which means they can pass on that to their customers, us, right? So optimizing the flow of oranges or apples, or optimizing the flow of parts through a factory to build a car, or optimizing the flow of information through an organization from idea through into the realization of that idea and hopefully a customer saying thank you. I like Dan North's definition of the purpose of a team is to safely and sustainably reduce the lead time to thank you. I think that's a nice idea. It's not enough to get into production. Someone should be happy and should be pleased to be using the things that we've built. So pretty much all work, all activity is about these systems of flow, stuff flowing from ideas through into production or from raw goods into via a series of value-adding activities into finished products. Right, that's pretty much what I mean when I say flow. Your definition may vary, but this is the one I'll be sticking with in this talk. So this is me, clearly, in my younger days. I couldn't find a grey, what are these called, like plushy toy, Chewbacca, unfortunately, but it turns out I used to look very much like this before I got a bit older, and now I look like this. I've done some stuff over the years, probably most well-known for the paper I wrote with Martin Fowler on microservices some time ago, back in 2014, which was sort of the original definition of microservices. These days, I've been writing about legacy displacement patterns, also on Martin's site, with 2 of my colleagues, Rob and Ian. If you're interested in how to move away from legacy and you're not satisfied with the standard answer, which is, oh, you used the strangler vine pattern. Well, yes, but what does that actually mean, right? So we're trying to explore that in some writing on Martin's site. And just to show that I'm an equal opportunities geek, and for Sam Newman, who's not in the room, I don't think, but for Sam Newman, this is me at Warhammer World in Nottingham. I'm also an avid Warhammer 40,000 painter and collector, so it's not just Star Wars and Lego, just saying. Maybe there's a 40K talk I should do at some point. Now, witness the firepower of this fully operational conference talk. A long time ago, well, it wasn't a long time ago in a galaxy far, far away. It was a long time ago in an office far, far away. So basically what happened was, a long time ago, 10 plus years ago now, we were doing some work for Lego in Billund. The company I worked for, ThoughtWorks, were a consultancy, and we were asked to help them solve a bit of a gnarly problem they had. They had a couple of gnarly problems, one of which, and I kid you not, was around genitalia detection in a massively multiplayer online game. Now, it turns out, if you're Lego and you have a massively multiplayer game in which the idea is to collect bricks and then you build structures locally on your client, and then you kind of publish the structure you've built so that everyone in the world can see the structure you've built, and you hand that to a bunch of 10-year-old boys, guess what happens? I won't go into it in any more detail. Turns out it's a thorny problem to try and to solve that. And this is back before we had access to racks and racks of GPUs on demand from AWS or from Azure, right? So interesting problems to solve. And as a thank you, they sent us at the time, what was the biggest set they produced, which was the Ultimate Collector's Edition Millennium Falcon. And that sat in our office for a little while, until one Christmas, when there were a few of us, we call it being on the beach. It feels nicer than on the bench, which other consultancies use. We were on the beach, I was on the beach with a few others, and we decided to get together and build this thing. We'll have a go at building this and let's see what happens. So a long time ago, in an office far, far away, Lean Lego. I haven't got the rights to the music. I can sing it, and I'm Welsh, so I've got a pretty good singing voice, but it's probably not up to the Star Wars theme, so you just have to imagine that playing in your mind. I'm sure you can. So episode 4, a new box. As I said, we got this box delivered to the office. This is the box. This is a very battered-looking version after some years in the office. There are some notable features of this. If you are an adult friend of Lego, you'll probably understand that some of these are quite big and quite complicated. 16 plus is the recommended age for building this thing. There was a 300-page double-sided manual. If you've not been amongst these big Lego sets, they tend to get big manuals, 300 double-sided pages of manual, and more than 5,000 pieces. Now, these days, it's up in the 7,500 count, I think, even some more for the biggest sets. But this, at the time, was the biggest set. The current version of this comes in a box that's so big and heavy, it's got built-in wheels, that you can wheel it out the store, which is pretty cool. But 5,000 pieces, all in this box, in bags and so on. This is the team. These are myself and some colleagues of mine who've decided one Christmas to build this Lego set. Before I get into how we got on, I did promise you that there would be some stuff that might teach you something, maybe some stuff to take away. So I'll just go into a brief science bit, which will go from stuff that's obvious, probably, to maybe stuff that's not so obvious. So the first thing I'm going to like to call out is the idea of a story wall. So visualizing your system of work, right? Visualizing the steps, the activities, the value-adding processes that your team will go through as they're delivering, essentially what is, information of some sort into software that goes into production. And story walls in general have a number of features. You can see in this, there's a bunch of sort of red cards, which are defects. There's a bunch of blue story cards. We tend to use user stories in ThoughtWorks. And they also have these swim lanes, right? So here we've got ready for dev, in development, ready for QA, in QA. So the key thing to call out here is we haven't just got in dev, in QA done. We've got these ready for states, right? Ready for dev. Essentially, we've got queues in the system. We're visualizing queues of work that are ready to be processed, if you like, by the people doing the work. But people have seen these, I'm sure. Most organizations use these in some form. If you're not doing it physically anymore in an office, then probably on something like Jira or other tools are available, Trello, etc. So the next thing is burn-up charts. So these are pretty standard as well, right? Generally in Scrum, they call them, or have done traditionally, called them burn-down charts. So what this tells you is how close you are to achieving the delivery of the scope that you signed up for. And in Scrum, as I say, you have the total number of scope, and every week you burn down to, until you finish. In ThoughtWorks, because we're a bit awkward, frankly, but also kind of this sort of style of Agile we do kind of predates Scrum as well. We don't use that, we use burn up. On the basis that if you burn up to something, you can also do things like visualize when you add scope, or when scope is removed and so on, much more easily. So in this, you can see, this is an example from a project I was on. This was a retailer, actually, a 3-month project. And you can see that the total scope started off at 114, and then it ended up a lot higher. And you can actually plot that much more easily when you're burning up your velocity cumulatively towards the total. As you can see, we sort of migrate up towards it until we finally reached our end date in iteration 8. We burned up to the total scope. Pretty straightforward, right? This is pretty simple set of tools that most people, I'm sure, are familiar with. Now we're coming on to some that not everyone has come across before. So I'll take a quick poll. Who's come across cumulative flow diagrams? Got two hands in the room. So again, these are a super useful way of understanding how work is flowing through your system of work. And what you plot on a cumulative flow diagram, you plot your cumulative velocity, say, but for each stage in your process. So you track, how much work is being done by QA, how much work is being done by dev, how much work is being done by analysis on the same diagram. So it's a bit like a burn-up chart, except with much more detail. And these show you interesting things because they're able to show you things like whether whether the work that's coming into your development team is outpacing the work leaving your development team. That is, whether the rate of arrival of work is different to the rate of departure of work. We'll come on to that in a bit. And this is another example of a cumulative flow diagram from a software project, right? And what we can see on this is interesting. So this is, as I say, this is plotting each of the stages independently. So velocity is the total of all of this, but what you see is it's broken down by the individual stages of the development team that the development team go through. And this gives you lots of information about where blockages are, right? So it gives you information, for example, I think it's the pinky bit, which is highlighted by the arrow. This is stuff that's been showcased, but is not in production yet. It's just sitting there, doing nothing, right? It's been signed off, yes, this is what we want. But it's not making you any money. It's not making the customers thank you. And this highlights these sorts of blockages, all things that have been signed off but haven't been showcased, these sort of ideas. So what this allows you to do is visualize when, for example, you've got a lot of development activity that's happened, but it's outpaced your capacity to test it. Because stuff will build up before test, and you'll see it on the cumulative flow diagram. Now, this is another tool that I use practically daily. But again, isn't that obvious to many people, or many folk haven't come across it? Who uses value stream mapping, or has value stream mapped their organizational flows? There you go, we've got 1, 2 people. Again, a value stream map, this became popular from the Toyota production system, lean manufacturing. And what value stream maps show is the system in which you work and the amount of time it takes to perform the different activities in that system. So this, for example, we've got 3 activities. Maybe it's the 3 days. The first one is development, the next one is testing, and the final one is deployment. And what that says is, on average, we take 3 days to develop something. On average, it takes a day and a half to test it. And on average, it takes half a day to deploy it. Right? But what you also plot on the value stream maps is how long you have to wait, work waits between transitioning between the activities. So if you like, it's another view of the cumulative flow diagram. So what this one says is, there's 10 days that a piece of work sits after being developed before it's tested, doing nothing, right? It's building inventory, and you've got a holding cost associated with that. You've got 30 days then when something is tested, but before it gets deployed. So, of the total of that, the length of that process, 30, 42, 47 days of activities, only, 3, 4.5, 5 of those days are actually giving you any value. The rest of it, stuff is just sitting around, not making you any money, getting stale, getting old, essentially. And value stream maps are super useful for development processes. We've had them on the ThoughtWorks radar for mapping your path to production. So you can look at, from requirements all the way through to deployment to thank you. Where are the waiting bits? Where are the bits where work is sitting there, not earning you money and potentially becoming old? Requirements go out of date, for example. So you've got the value creating or cycle time, you've got the wait times, and then the whole thing is known as production lead time. This is different to the DORA metric lead time. In the DORA metrics, lead time is defined as from commit through into production. Right? But the production lead time is the whole process, from idea through into thank you. All right, yeah, and in this case, as I say, you've got, 42 days where stuff is just sitting around waiting for stuff to happen. This is an example from a bigger organization I worked for. It's a big retailer. You can see down one end, down this end is the ideas happening. It goes through a set of requirements, validation, and business requirement documentation, and architect approval processes. And this bit, I love this bit in the middle, where it goes round and round and round. Two different teams of data architects, each who've got their own canonical model, data model, and they just go around and round updating each other's models for a bit. I don't know why, and then afterwards nothing happens and something pops out. There's one post-it on here. If you can see, there's one little blue post-it. That's someone writing code. That whole process is probably 18 months, and one little bit of writing code. Yeah. They didn't, I think, understand what canonical meant as well, the canonical data model people with two of them. So, these are very useful for understanding how work flows through your organization and through your teams. And having these enables you to make interesting decisions. In fact, we didn't have to go as far as putting all the numbers on this, because we showed this to the IT director when it was in this sort of state. And he took one look at it and said, well, clearly we need to make some changes. You don't need precise measurements of these things. You just need to understand the breadth of stuff that happens and work to optimize it. Finally, in the science bit, control charts. I'm not sure if come across control charts before. No one. So this is, hands up if you've heard of Six Sigma, Lean Six Sigma. Right, so we've got quite a few hands there. So Six Sigma, again, from Toyota Production System, from lean manufacturing, they make heavy use of control charts. What control charts do is allow you to understand how variable your system of work is. We've all been in the situation, we're on a team, right? And 1 week we're doing the velocity, which is like 10 points for say. The next week it's 11 points. The next week it's 8 points. Well, your natural variability on that team is going to be hovering around the 8 to 11 point mark. You should expect in the future probably to be doing 8 to 11 points. You shouldn't predict outcomes based on suddenly doing 25 points, right? Because the natural system in which you're in is probably going to mean you're doing 8 to 10 points. But the other cool thing about these is they allow you to monitor for exceptions, for stuff that's outside the norm, right? This is an example. So say, for example, you're on a team and you're doing velocity around about 10 most days, most weeks, but then suddenly you have a week when it's 20. Okay, well, that's weird. Why have we suddenly got a week when it's 20? So you can go and have a look and understand what circumstances were when you had this sudden leap in productivity. It turns out maybe that week all the stories were really small or something like that, right? So you just roll through them really fast. And then later on, we've got this dip down to a velocity of 1. Well, it turns out, what happened there? Lots of really small stories. And you can go down to this velocity of 1, where maybe someone left the team. Maybe the team shape changed, right? Maybe something happened, maybe loads of people were on holiday, maybe it's Christmas. What these help you to do is answer the question which a lot of organizations struggle with, which is justifying, if you like, why things sometimes faster and sometimes slower. Right? Because it's just natural. You have a natural variability, and it also allows you as a team to reflect on why things were sometimes slower or sometimes faster. But in a deliberate way, not in a way that you have to look at everything, just the interesting specifics. And the reason I've got the sigmas up there is you have these things called upper and lower control limits. And they're 3 standard deviations away from the mean. And that's where Six Sigma comes from, the name. The 3 standard deviations away from the mean on the control chart. Right, back to Star Wars, because you're like, I thought it was going to be Star Wars on Lego, not graphs. Blimey, James. Episode 5, The Lego Strikes Back. So as I say, we got together at Christmas, we took a look at the first set of instructions, and we all suddenly just piled into the box. It was like, oh yeah, Lego, there's stuff going everywhere, people are just finding stuff, and it's like, yeah, this is super exciting, everyone putting stuff together. Well, we're having a great time, right? Really great time. But the problem is it went really, really slowly, right? Really, really slowly. See, so this is the Lego system of work, right? Plotted on a value stream map. Basically, it's pretty straightforward. You have to find bits for a stage, then you have to assemble the bits. That's the Lego system of work. It's pretty simple. And what was happening was it was taking ages for us to find stuff, and it was taking quite a long time for us to put stuff together. So that's my first tip, is understand the system that you're working in. Right? And sometimes we're guilty of being too in the moment. Right? We don't think, we're too, I heard the phrase, we're too busy doing the work to think about how we do the work. And so the first thing is to think about how we are doing the work. Take some time to actually understand the system. Visualize it. Use these tools that I've been talking about. It turns out what was happening is we were processing this work serially, right? So we were all picking up something from the backlog, like the next stage in the manual. We were all finding the bits, stepping all over each other's feet, and is this it? No, it's not. Oh, I found this one. Well, so have I. Which one? Whatever. And then we were all putting stuff together. We're sort of processing this work serially. That's my next tip, right? Use Kanban boards or story walls to visualize your system. And this is true post-pandemic as it was true pre-pandemic. ThoughtWorks are a massive fan, as many teams are, many organizations are, of big visible charts, right? Get everything on the wall. Get everything now onto Mural or Miro, so that everyone's got access to all the information all the time. I mean, the number of times that people have just walked past a storyboard on one of our teams and sort of gone, well, why is that doing that? I could help with that, and unblock something just because stuff was visible. Ditto for build radiators, ditto for holiday schedules and all these things. Make stuff as visual as you can. And Kanban boards and story walls are a great way of doing that. So the result of all this, well, on our burn-up chart, it wasn't looking great. It turned out we were going to be finishing around about the heat death of the universe. That sucks. Something had to change. We had to do something about it. Sad face. So you can tell how old this is, right? Just, sidebar here, right? Breaking the fourth wall. You can tell how old this is because it was pre-memes. Right? We didn't have memes back when I wrote this. Right? That's the thing. Just saying, Episode 6, The Return of the Processed Jedis. So a funny thing happened, right? So this is our system of work, finding pieces for a step, and assembling pieces for a step. So we moved from basically everyone finding stuff followed by everyone putting stuff together to a slightly more evolved version, which had a big impact. We had a certain number of people that were finding stuff and a certain number of people that were putting stuff together, basically. Really simple change. We split the team. We'll just concentrate on finding things. You concentrate on putting stuff together. And we got a lot faster. You can see this is an accurate a visualization of us doing these things, as I say. I took all the photos, incidentally. I was really pleased with myself. So what we did is we identified a constraint in the system, right? So we identified the fact that it was taking us a long time with all of us trying to find particular pieces and all of us trying to put stuff together. So we identified this constraint, and then we worked to try and move that constraint or eliminate that bottleneck, work to reduce that bottleneck. It turns out you can actually find pieces in parallel. Right? You don't have to, everyone find the bits for the next stage in the manual. Some people can be doing that, but you can look ahead if you like. So I'll be looking at stage 1, my friend will be looking at stage 2, someone else will be looking at stage 3. So you sort of parallelize the process of finding stuff. So that's my next tip. Use the theory of constraints. Now, again, this is another hands-up moment. Have people in the room come across the Phoenix Project? Phoenix Project, yeah, I have quite a few people. It's great. It's a business parable about what we do, about an IT department, and how blockages form in the flow of work in IT departments. But of course, it's a rewrite of an earlier book called The Goal, written by a sort of famous management consultant, actually, he wasn't US, he was, I think he was an Israeli management consultant called Eli Goldratt. And he wrote this book called The Goal, which was about a manufacturing plant. And the manager of, there's a guy who's promoted to be manager of the manufacturing plant, but then he gets a call from his boss, and the boss says, everything's broken, everything's going too slowly, we're going to have to shut your plant in a month unless you turn things around. And the goal is a story of how he uses this idea of the theory of constraints to turn the factory around, to improve the flow of raw materials through into finished products in his factory. And it's quite funny as well, because he's like the person he leans on. He meets some dude in a bar, it's always a dude, who turns out to be a physicist, like a jobbing physicist, who sort of Socratically teaches him how to unblock the processes by sort of drip feeding him information. And then he drives off in a red sports car. But this idea of the theory of constraints is really, 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 really powerful. Because any system that you're in, there is always going to be a constraint. Always. You can't get rid of the constraints just move around. So, if you've got one machine that's going slowly, you can maximize the output of that one machine, but then it's producing more stuff. So the next machine might be then moving, producing stuff too slowly. So the constraint is moved from one machine to another machine. You see this in software development all the time on our teams, right? We'll be working as a developer writing code, and suddenly there's a big build-up of user stories because, I don't know, maybe some people were on holiday, capacity's down, you hit a thorny problem, something happens, right? So that the development process, writing code, is the constraint. But when that constraint is alleviated, or you remove that constraint, maybe by people come back from holiday, or you add more developers to the team, suddenly the constraint moves to QA, right? And there's not enough QAs to process the development work that's been done. There is always a constraint. There will always be a bottleneck in every system in which you work. It's a question of identifying those constraints and working to minimize them. It's like whack-a-mole, though. You're always going to have something pop up further up the line. So a funny thing also happened. We had this idea of queues. I mentioned right at the start, this idea of queued states on a storyboard, not just having in development, in QA, and done, but having ready for development, in development, ready for QA, in QA. Those ready for states are essentially queues of work that are waiting to be picked up by the next activity, by the next stage in the development process. A funny thing happened, this. We started to create these queued states in our system of Lego building because we would run ahead, the people would be putting stuff together, and that was a fixed, cost or a fixed time. You could only do one of those at any one point, really. Come to that later. But you could find stuff in parallel, as I said. So we started to get a set of a queue building up of pieces that were ready to be assembled, if you like. So we visualized that queue in our system, essentially, based on the pages of the manual. Right? In this case, we visualized a queue by having this queued state on a storyboard, but in the Star Wars case, in the Lego case, the manual and the stages in the manual became the natural point for us to place the stuff that was waiting to be built. So we had these queued states based on the pages in the manual. And the folks who were putting stuff together, they pulled from the queue, the thing that was at the top of the queue, the next stage, and the people finding bits pushed into the queue. And this is a key thing, actually. Another tip. So identifying queues is the best way, in fact, of controlling our cycle times. When I talk about cycle time is it related to lead time? Well, cycle time is the activity for a particular process to happen, right? We're talking about it's the best way of controlling, essentially, controlling how long our lead times, how long it takes to get stuff through the system. And you might think that capacity, adding more people, would be the best way of doing it. You might think that, like measuring cycle time itself, and then acting when cycle time blows out was the best way of controlling it. But actually, queues are a leading indicator of all these different things. They're a leading indicator of a lack of capacity. They're a leading indicator of your cycle time blowing out. This is from the brilliant book, if you haven't come across it, Principles of Product Development Flow. I read this first back in about 2008, I think. Dan North handed me a copy when I was on a team with him, and he said, read this, it's amazing. And I've read it, and much like the first time I read the Gang of Four design patterns as a junior developer, I kind of read the Gang of Four, and I went, well, that's kind of interesting, but I don't really get why it's so groundbreaking. But then when I read it later, when I was been developing software for a while, it's like, whoa, this is really cool. Patterns are a useful way of categorizing and assembling information. Same thing happened for me with this book, Principles of Product Development Flow. I read it back in 2007-8, and I was kind of like, yeah, kind of, okay, that's interesting. And then I read it about 2017. I was going to a conference where Don Reinertsen was presenting, and I thought, I better reread it so I can have a conversation with him about it. And it blew my mind. It's probably the most important book I've personally read about what we do, about knowledge work, about the idea, about how we take ideas and turn these ideas into valuable software. And what's in one of the principles in Don Robertson's book is the queue size control principle, the second one. Don't control cycle time, control queue size. Don't control the lead times, if you like. Don't control how long it's going to take to go from commit through into production. Control how much stuff is waiting to be committed. Like, control how much work is waiting to be fed into the development team. I'll give you an example of this because it's quite subtle. And actually, we'll come to that in a sec. So this is conferences. We all go to conferences. I'm sure we're all at a conference, which is, a useful indicator that we all go to conferences. You probably go to other conferences as well. Now, NDC does something quite different to most conferences. So most conferences, what happens is you've got a bunch of people milling around, in the vendor area, in the expo area. You've got the people who are working on the stalls and so on, and they get hungry, and about lunchtime, lunch is served, right? So, when lunch is served, basically, the people who are milling around, they start going to the, they form a queue at the buffet, they start getting some food, and then suddenly the sessions end. Right? And you get this massive influx of people, suddenly all hungry, suddenly all wanting food. So what we've got here is a graph that shows the arrivals into the queue in front of the buffet. Right? So you've got this sort of steady state of arrivals, and then suddenly a whole bunch of people turn up, and then it goes back to a steady state. But the departures from the queue, the capacity of the buffet table, if you like, to serve those people is constant. Right? It doesn't vary based on the number of people waiting. Right? It's a constant departure time with a variable arrival time. So the sessions finish. Now, if we were to think about taking action to speed up this process by looking at cycle time, we wouldn't notice the cycle time change until about 1:35 on this graph. It takes quite a long time for us to be able to see that a cycle time has changed. But if we just measure queue depth, if we just look at the number of people waiting, instantly, we know we're going to have a problem down the line. And that's why Don Robertson says, look at cycle time. Look at the stuff that's waiting to be done, the work that's waiting to happen, not how long it's going to take to get done. Right? And control the amount of stuff that's waiting to be done. So what does that mean? That means minimizing the number of projects that are ongoing at once, minimizing the amount of work that's sitting in front of your development team and in front of your QA team and so on. Can anyone tell me why NDC have solved this problem? Or how they've solved this problem? All-day food, right? So it's a solution to exactly this problem that every other conference that doesn't do all-day food they have this problem. NDC doesn't really have this problem, or has a much, much smaller version of this problem. Because, yes, people are generally going to get hungry at lunchtime, but the demand is smeared out over a much wider time frame. So control queue size, not cycle time. And by doing some of these things, we got faster, right? So this is now we're measuring progress in hours. On a burn-up, we're not measuring it in pigs flying and heat death of the universe, which is good. We're making some progress. So that's my next tip. We can use burn-up charts and yesterday's weather to track progress, right? I'm not sure if everyone, have a drink of water. I'm not sure if the origin of the phrase yesterday's weather in agile software development has been lost in the mists of time. But it comes from this idea that if you plan when you're leaving the house today, if you plan to take an umbrella or the clothes you're going to wear based on the weather yesterday, you're going to be right about 70% of the time. So that's why we say in agile planning, plan using yesterday's weather. Plan for tomorrow based on what we did yesterday and the day before and the day before, or last week and the week before and the week before. And expecting, as I say, suddenly go from, on average, 10 points a week to 30 points a week, because that's what the deadline says we need to do, is completely unrealistic, right? It also gives us an interesting way of prediction, right? Predicting when we're going to get done based on actual results, not based on guesswork, or still guesswork, but not based on kind of the magic idea that everyone towards a deadline will suddenly become 4 times more productive. So we can use these techniques to track progress. But we didn't stop there. Some other interesting stuff happened. The team became kind of T-shaped. I'm sure you've come across this idea of T-shaping, right? Generalized specialists, or generalizing specialists. Personally, I'm pretty deep on software architecture. I'm pretty deep on design. I'm very deep, if you like, in terms of skill set on Java 1.4. That's a bit old now. I'm pretty good on C#. I'm pretty good at a majority of programming languages. I'm terrible at Haskell. Not very good at Haskell. I'm okay at Clojure. And actually, I can pretend to be a QA for a bit if I need to. Right? So I'm deep in a certain set of things. But I'm also broad across other skill sets. I can pretend to be a QA for a bit. My former colleague, Jeremy Sutherland, he used to say, when a project's kicking off or a product's starting, I can pretend to be an enterprise architect for about 2 weeks. Then they find me out, and I need a real one. But for about 2 weeks, I can kind of pretend. And that's this idea of a generalizing specialist, being able to do a little bit of other stuff when your team might need it. I'm not a QA. I'm never going to be a QA. My brain doesn't work the same way that really good QAs work. Right? I remember the best bug report I ever saw. I can't remember which. It was one of the investment banks. And there was a bug, there was a defect raised, which was if you put more than 32,000 whatever characters into the password field, you get a 500 exception. But I'm never going to try and test putting 32,000 plus characters into a password field to see what happens. But good QAs, that's what their brain does. That's how they think. But I can still help. I can still help the QAs if I need to. And what we ended up with is we had a bunch of, as I say, specialists in assembling and specialists in finding pieces. And the reason we had specialists, I guess, when you're building these big Lego sets, when you're putting them together, it actually helps if you're just putting them together, because they're quite complex topological problems, right? They're quite big, and there's lots of hard bits, and you have to so you actually get better at doing it. You can get to visualize the problem that you're trying to solve. And the people who were finding bits, they got better at finding them because, I thought I saw that bit that I need now a couple of minutes ago. I'm going to have a look there. Yes, there it is, You have this memory of where the bits that you were looking for might be. So we had these sort of specialists. But it didn't mean that, if something happened, the people who were finding stuff couldn't help the people who were putting stuff together. Or the other way around. If we couldn't find one tiny little bit, everyone sort of helped by looking for it. So you have this idea of generalizing specialists and T-shaping. And those specialists noticed something interesting. So this is a control chart, plot of the length of time it takes to find a piece. As you can see, the variability is all over the place. When you see charts like this, control charts like this, it means your system variability is such that you can't really predict with any accuracy what's going to be happening in the future. Right? Things are just too variable. Things are just too volatile. I mean, this is why traders like volatility, right? This is why when you look at stocks and you see shapes like this, traders like rubbing their hands. I can make money off this, right? The volatility is high. Right? But these systems mean it's very difficult to make predictions about them. It turns out when you're looking for Lego, right, finding a piece is a function of two things. It's a function of how big the piece is and how many of them you've got. Basically, if you've got a tiny thing and you've only got one of them in a set of 5,000 bits of Lego, it's going to take you a lot longer, unless you're super lucky, to find than 50 of these big plates. They're kind of obvious. So these small things take longer to find than this, and that was leading to this massive variability in how long it took us to find these bits. So we sort of just in time started creating this inventory in front of the finding pieces activity. We started grouping like things together. So we started putting all the 8x1 peg things in the same pot and all that sort of stuff. But we did it just in time. We didn't do it at the start and just sort everything into these pots. Maybe we should have done. I'll come to that later. But we started creating these little these cups of similar pieces. And that led to a much less variable process. Suddenly, we had a much easier way, a more predictable way of finding these bits in much shorter time. So that's my next tip. Tip number 6. Use control charts to identify variability in your process and then work to reduce it. Now, maybe this is a naughty people bit, but a lot of the teams I spend time with, they've sort of forgotten the power of things like hand-drawn charts or creating, doing analysis on the process in which you're working yourselves, and tend to rely too much on, well, what does Jira give me? Oh, Jira gives me a burn-up chart, cool, that's what I'll use to track progress. There's a real power in actually using some of these other techniques that aren't necessarily just included out of the box. And in fact, I quite like, in the before times, when I was a tech leader or whatever, I used to have a ceremony to the start of every iteration, rather than just have a printout of last week's velocity and the burn-up on the wall. I would have a hand-drawn A3 graph, and the ceremony was at the start of the iteration, the first showcase. Someone would go up and mark on the hand-drawn chart where we got to. And I know that sounds like a really small thing, but it serves dual purposes. Obviously, it communicates how we're doing, but it also means we get to celebrate our success, celebrate that we've achieved some stuff, and it also means it's an easy starter for a conversation about why we didn't maybe go as quickly as we thought we would, or get as much stuff done, or why we got more stuff done. So use control charts and just make things visible in general, and work to reduce variability. Other fun things happening, we have defect tracking. So this is from the actual thing. This is one of the defect cards we had. We had two types of defect. This is, as you can see, a non-critical defect. So what we would do is identify what part it was that was missing, that we couldn't find, essentially. We would note what page of the manual. But if it was non-critical, it meant it was cosmetic. We could carry on, right? And hopefully at some point we'd find that bit and just add it. We also had critical defects, and-on cords, pull the and-on cord, stop the line. We can't go any further because we can't make any more of the model without this thing. So then all the team would start looking for it. And, in the same way that you should swarm around things like, your build breaking, right? That's an and-on cord, that's a stop the line. The team fixes the build, or at least give someone the stupid penguin hat to fix the build, or whatever you do. Your stupid hats may vary, but I like penguins. So we had these defects, they were kind of useful. And we also had work in progress limits, WIP limits. So we controlled, as I say, the queue size, not the cycle time. So can anyone spot the natural work in progress limit in this system of work, the Lego system of work, where we're putting bits on the pages of the Lego manual? Exactly, you can't turn the page, right? So you can only get so far ahead as turning the next page. You can only have so much work, like waiting to be done, so much stuff in your queue, because otherwise stuff's going to go everywhere again. But this is a super, super powerful technique to control cycle time, control the amount of stuff that's waiting to be done. Right? So if you've got, in this case, 4 items waiting to be developed or waiting to be built, you don't push any more stuff into that queue. Right? Instead, you go upstream and try and unblock the problems that's causing that queue to build up in the first place. And we swarmed around bottlenecks. So if we couldn't find something that was important, we all swarmed around it. So limit work in progress and then pull more work from upstream if you're blocked. And there's the burn-up chart. Yay! At this point, memes started to happen. So Chewie, we're home. And that's the finished result, the finished build of the Millennium Falcon. Woo! And unicorns, and I got a bit meme obsessed then. It was of a time, right? I mean, this was of a time. This meme. So conclusions so far, right? So understand your system. So this is the point that I came to a number of years ago, right? So understand your system. Use these system thinking tools to understand how the system of work works. Value stream maps, things like storyboards, that kind of stuff. Visualize work using Kanban boards and story walls. Continually work to identify constraints in your system. Right? So use the theory of constraints. Understand there's always going to be a bottleneck. Always be looking for the bottleneck. Allow yourself some time to think about how you're doing the work, not just to do the work. Right? That's a really crucial thing. Then you can use this idea of queues. You can use the idea of controlling queue size, limiting work in progress, and swarming. That helps us keep throughput high. Because it's all about removing blockages, all about the flow of work through to the customer saying thank you. And then we can use yesterday's weather and burn up to track progress and use control charts to identify and reduce variability. Fine. Now, episodes 7, 8, and 9. Like 4, 5, and 6, but newer. Oh, hi. Now, this is the only time I've ever been able to expense a Lego set, but I figured because it was for a keynote, for a conference, then I'd be able to expense it. So I went out and bought a Lego set. It wasn't a Star Wars Lego set. In this case, it was these folk, I can't even remember what they're called now. Nexo Knights, that's it. And this is the Lego set I bought. Because I wanted to see what had happened in the intervening years, whether Lego had actually changed anything about the Lego system of work itself. So I picked up this Lego set. My son was really into Nexo Knights at the time, so it felt like the appropriate thing. So here's the question for you. If you were Lego and you were also constantly learning from the experience of building Lego sets, right? Because that's how they play. You know, the designers are playing all the time. People in Lego are playing all the time, learning how best to do stuff. So if you were Lego and you were constantly learning, what would be the change that would have the biggest impact to the Lego system of work? Pre-bagging pieces. Pre-bagging pieces. Any other answers? Sorry? Removable pages, bigger queues. Yeah. And also you can put them into, I don't know, laminate them as well, maybe. I don't know. If you've got removable pages. Any others? PDFs. Absolutely. PDFs as the manuals. That's another innovation they've brought in. Yeah. All good ideas. I want to point to the guy who came up with the first answer there, because at the start, right, back in the day, Lego used to be sold in these big boxes with all the pieces in like just random bags, right? Sometimes it was all the same together, usually not. Often it was just, just a bunch of stuff that came out of the factory that they dumped into the box. What we did to optimize how quickly we were able to process Lego, if you like, to build Lego, is we started putting like things together. So there's another bit of a sort of science sidebar here. So this is, again, from the principles of product development flow, the batch size queuing principle. Reducing batch size reduces cycle time. Again, from Don Reinaldson. So what does he mean by batch size? In batch size in software development, this is what we talk about in terms of the amount of requirements that move from one stage of a process to another, right? Classically, a waterfall process is going to be like 100% batch. So all of the requirements are, you have a business requirements document. All of the stuff is analyzed by your analysts. And then all of that stuff is given to the developers. The developers do all of that stuff. And then they hand it to the QAs who test all of that stuff, who then put all of that stuff into production, or via probably regression and integration and performance and all the other stages you would generally go through. But that's a batch size of 100%. All the requirements have to be done by one stage of the process before moving on. In contrast to that, a single-piece flow system, right, which is essentially lean or agile, if you like, continuous delivery is a single-piece flow system. As soon as something is ready from the previous stage, it's able to be passed to the next stage, where it can be picked up. And the idea is you should be able to pull one of these things all the way through, single-piece flow. The smallest batch size number is 1, the smallest item in your backlog, essentially. So what the batch size queuing principle says is just by reducing the size of batch you pass between process stages, you improve cycle time. You get faster just by reducing the batch size. Right? You make more money just by controlling batch size. So there's a graph that shows essentially a process which has 2 batches of requirements going into production. Right? You've got time, you've got one batch which takes a length of time to be developed and then is put into production, and you've got another batch that is developed and put into production. Right? And as you can see, the time it takes to put something into production is totally dependent on the amount of stuff in the batch. Now, when you think about single-piece flow, continuous delivery, agile software development, these sort of processes, it's all about reducing the amount of stuff that goes through each of these processes. So as you can see, in this case, we've got lots of small batches. I'm going to come over this side, I'll go to the other side in a sec. This stuff goes into production at this time. It's earning money already, as opposed to having to wait all the way to here to start earning money. This stuff goes into production here. It's earning money instead of having to wait to that point. Just by controlling batch size, you control your cycle time, improve cycle time. Another quote from Don: batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. Without people working harder or adding more people, by halving the batch size, you double throughput. And that's really why continuous delivery is such an effective way of delivering software. Forget about the risks and forget about all that sort of stuff. Batch size reduction is at the heart of it all. He goes on to say the effect of queues, so stuff that's sitting in a batch waiting for something to happen. You get longer cycle times, you get increased risk, more variability, yada, yada, yada. Pointing to my good friend in the fifth row back, that's what Lego did. Lego controlled batch size. So they start now putting smaller bags together of just the first 10 pages. So they control the amount of stuff you've got to look through in order to find a piece to start building. They did something else which no one mentioned, but these days a lot of Lego sets are modular. You have these modular buildings, but also the other sets tend to be modular. You tend to be able to build bits of them independently and clip them together later. And that's related to something called the fluidity principle, again from Don Reinertsen. Loose coupling between product subsystems enables small batches. And this, of course, goes to the heart of my thinking around microservices such a long time ago, right? The fact that we can create these small things that are decoupled from one another, that we plug together, that was at the heart of the thinking behind microservices. Ta-da, it's done. So let's rework my tips from the first time I did this talk. So the first thing is understand your system. That still stands, right? Understand the system in which you're working. Visualize the queues in your system. Because by visualizing queues and understanding how much stuff you've got in queues, that allows you to understand your cycle time and how to control your cycle time more effectively. Identify constraints in your system. Use the theory of constraints. But interestingly, there is a limitation when it comes to product development. The theory of constraints was designed around manufacturing, where a machine does one thing. It makes a widget. Then it makes another widget. It makes another widget. Right? And so the theory of constraints is very useful in that circumstance. And it's useful for what we do, but it turns out we're humans. We're human machines. We can do other stuff. If someone says, hey, can you help out with QA for a bit because we've got a backlog of stuff needing testing, I don't have to say, no, I'm only able to write C#. Right? I can go and help testing. We can do other things. So understand the constraints, but understand that it's not all about the theory of constraints. Use work-in-progress limits in swarming, and then crucially, this idea of small batches directly impacting the cycle time. And then this idea of anti-fragility. Build stuff that can be composed of lots of smaller bits, and you can plug them together afterwards. So these are the references I sort of used for the theory parts of this book, if you like, of this talk. These are the books. I'll move on from that. So the question that I'd like you to walk away with, when you're faced with your own challenges and your own teams is, what would Lego do, essentially? And what Lego would do is they would use small batches. So just think about that. And that's me for today. Thank you very much. And thanks to NDC Oslo, / London. NDC London. Oops. But thanks very much for coming. I'm James. Cheers. Bye.